Welcome to our mathematics lesson. Today, we'll be learning about surds and fractional indices. These concepts are essential in advanced algebra and will help you solve more complex mathematical problems. Let's begin with surds. A surd is an expression that includes a root, such as a square root or cube root, that cannot be simplified to a rational number. For example, root 2, root 3, and root 5 are all surds because they are irrational numbers that cannot be expressed as simple fractions. Let's practice simplifying and working with surds. In our first example, we'll simplify the square root of 72. We start by finding the largest perfect square factor of 72. Since 36 is a perfect square, and 36 times 2 equals 72, we can rewrite the square root of 72 as the square root of 36 times 2. The square root of 36 is 6, so our answer is 6 times the square root of 2. In example 2, we'll learn how to add and subtract surds. We have the expression 4 root 5 plus 7 root 5 minus 2 root 5. When adding or subtracting surds, we can only combine like terms, which means the surds must be the same. In this case, all terms include root 5, so we can add the coefficients. For plus 7 minus 2, which equals 9. So our final answer is 9 root 5. Now, let's learn how to multiply surds in example 3. We need to find the product of root 3 and root 12. When multiplying surds, we multiply what's inside the root signs. So root 3 times root 12 equals the square root of 3 times 12, which is the square root of 36. Since 36 is a perfect square, the square root of 36 equals 6. In example 4, we'll learn an important technique called rationalizing the denominator. We have the fraction 3 divided by root 2. When we have a surd in the denominator, we multiply both the numerator and denominator by the same surd to eliminate the surd from the denominator. We multiply both top and bottom by root 2. In the numerator, we get 3 times root 2. In the denominator, we get root 2 times root 2, which equals 2. So our answer is 3 root 2 divided by 2, or 3 root 2 over 2. Now let's move on to the second part of our lesson, fractional indices. Fractional indices are a way of representing roots using index notation. The general rule is that a to the power of m over n equals the nth root of a to the power of m. This allows us to work with roots using the same rules we use for exponents. Let's practice with fractional indices. In example 5, we'll evaluate 81 to the power of 1/2. When we have a number to the power of 1/2, it's the same as taking the square root. So 81 to the power of 1/2 equals the square root of 81. The square root of 81 is 9. In example 6, we'll evaluate 64 to the power of 1/3. When a number is raised to the power of 1/3, it's the same as taking the cube root. So 64 to the power of 1/3 equals the cube root of 64. The cube root of 64 is 4, because 4 cubed equals 64. In example 7, we'll apply the general rule for fractional indices. Let's evaluate 16 to the power of 3/4. Using our rule, a to the power of m over n equals the nth root of a to the power of m, we can rewrite this as the fourth root of 16 to the power of 3. The fourth root of 16 is 2, because 2 to the power of 4 equals 16. So, the fourth root of 16 to the power of 3 equals 2 to the power of 3, which is 8. In example 8, we'll see how to combine powers. We need to calculate 25 to the power of 1/2 times 25 to the power of 1/2. When multiplying expressions with the same base, we add the exponents. So 25 to the power of 1/2 times 25 to the power of 1/2 equals 25 to the power of 1/2 plus 1/2, which is 25 to the power of 1. And 25 to the power of 1 is simply 25. Now let's try some more challenging, exam-style problems that combine the concepts we've learned so far. In example 9, we'll simplify a more complex surd expression. We need to simplify the fraction root 48 over 2. First, let's simplify the root 48 in the numerator. We can rewrite 48 as 16 times 3. So, root 48 equals root of 16 times 3, which equals root 16 times root 3. Since root 16 equals 4, we have 4 root 3. Now our expression is 4 root 3 over 2, which simplifies to 2 root 3. In example 10, we'll combine surds and indices. We need to evaluate 9 to the power of 3/2. Using our rule for fractional indices, we can rewrite this as the square root of 9 to the power of 3. The square root of 9 is 3. So, the square root of 9 to the power of 3 equals 3 to the power of 3, which is 27. In our final example, we'll tackle a more challenging problem: rationalizing a denominator with a binomial expression. We need to simplify the fraction 1 over root 3 plus 1. When we have a binomial with a surd in the denominator, we multiply both the numerator and denominator by the conjugate of the denominator. The conjugate of root 3 plus 1 is root 3 minus 1. So we multiply by root 3 minus 1 over root 3 minus 1. In the numerator, we get 1 times root 3 minus 1, which is root 3 minus 1. In the denominator, we have root 3 plus 1 times root 3 minus 1. This equals root 3 squared minus 1 squared, which is 3 minus 1, which equals 2. So our final answer is root 3 minus 1 over 2. Let's recap what we've learned in this lesson. We practiced simplifying and operating with surds, rationalizing denominators with single surds and binomial expressions, converting between fractional indices and surds, and applying these rules in exam-style problems. In our next lesson, we'll focus on expanding and factorizing expressions, which are essential tools for working with algebra. Thank you for watching.